Okay, welcome to this happy hour. Today we start a new series. It is called Scaling Software Builds Across Architectures with Automation. And today will be a little bit different, maybe from what you have seen in other happy hours. It will be a lot more abstract. There will be no demo, no code, hopefully. So it will be more just discussion of goals and design decisions behind a multi-architecture build board. Okay, so what we can see is that scientific computing depends on more and more software. So about 2 years ago, there was a publication in Nature. What they did is they analyzed about 2.4 million publications, and they found 100,000 unique software packages named. Probably many of you know PyPy. They have about 700,000 packages. CPAN for per package, they have 25,000. For R packages, there exist about 23,000. Julia has 10,000, and EasyBuild supports about 3,000 main software packages plus also thousands of extensions. So extensions are those what you probably get from PyPy, CPAN, or CRAN. What researchers expect is that the software just works on HPC systems. So when they go there, that what is probably installed there by admins, that it just works. And it should not only work there, but also on cloud instances, laptops, of course, if they have the same software there. What we do usually on HPC systems is that we build this from source. If you want to maintain the software stack, so that's time-consuming, error-prone, and a lot of duplicated work across sites. So easy, of course, is an answer for that, but it requires tooling, so that the sheer size of this is manageable. But the size alone is not a reason to automate this. So I don't know if anyone wants to speak up, but the question here at the bottom is how many installations do we have in EESSI today? And installation means any software package, any extension, any version on any architecture. Anyone who wants to say something or maybe write in the chat?
For me, next year. Early next year. But not yet.
Frank, I don't know if you want to mute yourself, Frank. Maybe I don't think that was an answer to my question.
Not exactly, no.
I can answer, but I'm not sure okay.
That would be for, yeah.
Yeah, it's. I don't know the exact numbers, but I think it's well over 10,000 by now.
Yeah. I mean, that would be not for any architecture, right? So that would be, I guess, only for single architecture.
Okay, then yeah, I don't know the exact number, but.
Yeah, so what I did is I just ran a check on checking all module files we have for all versions of EESSI. Of course, and also checking all the extensions we have installed in EESSI. And if you also consider that different versions count for different installations, then it's well above 100,000. Yeah, so that's a lot of software that's available via EESSI, and so we have to look into how to manage this, how to make this manageable. Okay, so here first I want to talk about sort of 10 goals we have when we talk about scaling software builds. The first thing is we should build consistently. Yeah? So it should be independent of whom triggers a build and where the build runs. Also, we need the builds to be reproducible. So So that means that sometimes when we have to rebuild something because maybe we found a bug or maybe some improvement, then we need to rebuild it, and that should be reproducible. Of course, automation is key. So we want to take humans out of the loop, particularly for repetitive work. So there's a little asterisk here because we don't want to fully automate the procedure. When it comes to efficiency, it is important that we have scarce resources, build resources, compute nodes, maybe even with GPUs, and we don't want to waste these resources. Of course, this also has to cope with more packages, more architectures being supported, using more sites for building, and also that we want maybe support more contributors. So that means the design should be scalable. If it is too hard to use, then only expert will do that, and that means it would become another bottleneck. So that we want to avoid that, of course. So ease of use is very important. It has to be flexible. So we want to support different scenarios, different workflows, building, testing, maybe other steps that are of interest in the future. If we run the bot on different sites, it has to cope with differences of the build sites. At some sites, the compute nodes have direct access to the internet. At some sites, they don't have. At some sites, you can run a container without loading a module. At some sites, you can't do this. And every site is a little bit different, and we have to cope with these differences. Security is, of course, very important. We want to prevent unwanted changes that may compromise the software stack. We want to have control over who actually triggers an action of the bot. And lastly, trustworthiness is also very important. You have to be confident that the installations are done correctly, and that there's no hidden magic somewhere that leads to a successful build. So that were, let's say, the goals. Now this is maybe a known picture. I don't want to spend too much time on this. So basically that's the workflow for adding software to EESSI. What I will now do is explaining a bit the design decisions behind a bot. So the first thing is about the interaction model. So how do we interact with the bot? We could say we just use plain CI, GitHub Actions. We could have maybe another option could be that we have some external tool, a command line interface, and then interact with the bot to trigger some actions, or we could have some GitHub app. And in the end, what we chose was to have a GitHub app plus also some scripts that understands structured commands and pull request commands, labels, and other actions like merging, closing, pull requests. When you talk about, look at the execution backend, so we can think of GitHub runners. We could think about self-hosted runners or external, or let's say other ways to run as a backend. So GitHub runners, of course, that would be nice because they're available, but the problem there is on what architectures we can build is very limited. And also we know that some builds, they take a very long time. So in the end, what we decided is that we use HPC clusters and we can use ones we have access to in our organization, or we can run create one on the cloud. And basically each cluster has its own running bot instance. So then we have to think about how we can declare for which architecture, CPU architecture, GPU architecture we want to build for. So that sort of tells is about for which we want to build to and where, and we decided to have to separate this into two arguments when we build. We can say we want to build for architecture, let's say Zen 2, and we would also then want to build on the architecture Zen 2. So you could ask maybe, okay, why do we need this additional on? Because if we want to build for Zen 2, maybe that's clear that we want to choose also this architecture. This is particularly useful when we want to build for GPU, when we want to build GPU software, because there we may not have all combinations of CPUs and GPU architectures. So there we would also allow cross compilation. The next design decision is about the build logic ownership. So that is about where the logic to build is included. Is it inside the bot or the target repository? So of course it could be inside the bot, and I think actually what we did is we started like this. When we started developing the bot, is that we included a lot of logic inside the bot, but that then was very specific to EESSI, and let's say even very specific to a single repository in EESSI. It was not very flexible. And we later then decided that the bot only defines an interface, and those who have a target repository like EESSI software layer, they define the actual logic in some specific scripts like bot build, bot/build.sh or bot/test.sh. Next is about the build environment. Should we build natively on a machine or in a container? And it was quickly clear that we have to use containers, and one reason is we have to make the /cmfs directory writable. By default, it's read-only. So if we would use what exists on a system under this directory, we cannot add software to that. With the container, we have also more control, what we can see inside that. And of course, we can build also on machines that don't even provide EESSI natively. And last, the reason there is maybe also that we can improve the performance. So we can use cached host-side libraries like CUDA installation and QNN and so on. Next is about system architecture. So how would we build such a system? Is it more monolithic, one single big application? Then maybe it's easy to share a state within that application, or more like a decoupled with different components, event-driven component. And what we have right now is that we have this different functions split up, and every component is responsible for some function. And I think the last is how do we do this? So build, deploy, ingest strategy. So let's say the three main steps maybe where maintainers of EESSI are involved. Do we do this fully automatic? Just because that, of course, would maybe scale more, or do we have some human in the loop? And I guess you can already guess what the answer is there is we do as much as possible automatic, but we allow and we need also some human involvement. Otherwise, yeah, it could happen that something gets added to the software stack that is not maybe correctly built, and we want to avoid that. So that was everything I wanted to say about at this high level. Next session would be about how it works, event triggers, build clusters, automated packaging at scale. That's more, I would think that goes more into looking at maybe some code, maybe some examples, more details there. And then I'm open for questions. And I don't see anything. I don't hear anything.
Maybe I have a quick question.
Yes.
So you mentioned we now have over 100,000 installations already, if you count all the CPU targets that we have, all the extensions. How long do you think it will take us to go to 1 million? And is that something we should aspire? Do we want to install as much as possible in EESSI, or?
Yeah, I don't know. So I would rather think that maybe having the ability to go there is maybe interesting, but not maybe so much the goal to reach that number. Yeah, so.
Yep.
So, for example, now we have started with a new version of EESSI 2025-06, and that's growing. And maybe at some point it will reach the same number of packages that the little older version has. So every software we have in EESSI now has been added to EESSI within 2 years. So yeah, but then if we can keep up with the pace and say adding a new version of EESSI every year, I think that would be very good. Yeah. If we can keep up with the number of architectures we have there, that would be also very good. And then I think it depends a lot on what users want to see in EESSI. If they want to see 100,000 more packages, then maybe we should be prepared for that. Questions?
Is there other making things easier to discover, for example, in things? We need to make sure it's easy to find your way among those things.
Yeah. Sorry, can you repeat the question? I didn't fully get it.
Yeah, maybe it was a bad connection. So if we do end up having 1 million things, are there other things we need to do to make it easier to discover what is there, to pick up on what is there, to combine things?
Yeah, that's a good point. So if you now initialize EESSI on your system and you run module avail, you see tons of packages, and maybe it's not so. If you already know what you're looking for, then it's fine, I guess. But if you don't know what of these thousands of packages provide what you want, then you're lost probably. So a way to find in the catalog what you actually want, that would be very helpful, I think.
So any concrete ideas on how we can improve that? Can we keep relying on the module system, or do we need a wrapper around it, or another tool on the side, or?
I mean, it depends a bit on. I guess there are different approaches. So, for example, when you look at Bash, and let's say you would know the executable name, yeah, but you don't know the module. You could do some automation that you just type the executable name, and then it will load the module automatically for you, and yeah. So that could work. But maybe that's not the best thing to do there. What you could do is maybe some tool that just helps you in finding the module.
Yeah. So you have the binary name, or maybe the name of a Python package you're missing, or and it essentially tells you where to or what the options are.
Or you could even think about like that. You could have something that you just ask, okay, I need some library that does X, Y, Z for me. What libraries exist and are they available and easy? And which modules do I have to load?
Does that mean like integration with LLMs that interpret your question and try to?
Yeah, that's the answer of today, I guess. Yeah.
No, but I mean there is room for something like this, right? We have
Yeah.
a ton of data on what is available in these installations, all the bits and pieces, even down to how things were configured, which features are enabled, what's compatible with what. So all of that would be
Yeah.
very difficult to make it easy to navigate.
I guess when it comes to LLM, the question is a bit where to run this LLM then. Yeah? So do you run it on your machine? Do you run it somewhere else? And it's a trusted service that you can just somehow connect by default when you initialize easy. So that's maybe also an interesting question.
Yep. Okay. Any other questions? Does anyone else have questions?
Okay, so what I would suggest is that I stop the recording and